Welcome to the direct comparison test. So the idea here, recall that for improper integrals, if we could essentially trap one region inside another, right? So if we had f of x, both positive, if we had 0 less than or equal to f of x, less than or equal to g of x, right? If basically f was trapped between 0 and g, then what we had was if the integral from 1 to infinity of g of x dx converged, right? Then the area inside it must also converge. So then the integral from 1 to infinity of f of x dx converged. I'm going to change this to converges instead of converged. And similarly, if the inside integral diverges, it's contained in the other one, so that must also diverge. So if the integral from 1 to infinity of f of x dx diverges, then the integral from 1 to infinity of g of x dx diverges. And so essentially, if we have finite area, then anything inside that must also be finite. If we have infinite area, then anything containing that must also be infinite. So we have the exact same test essentially for sums. So for sums, the equivalent direct comparison test, the direct comparison test for convergence of a series is equivalent. So essentially, if 0 is less than or equal to a sub n is less than or equal to b sub n for large values of n, it doesn't matter what's happening for the smaller values as long as this holds for the large values. Then we have if the series from n equals 1 to infinity of b sub n converges, so does the series from n equals 1 to infinity of a sub n. So this is equivalent to that first statement. If sort of the upper series converges, then the inside one has to converge. And then similarly, if the inside series diverges, so if the sum from n equals 1 to infinity of a sub n diverges, so does the sum from n equals 1 to infinity of b sub n. So this is essentially the equivalent. We saw with the integral comparison test how the sum is basically almost the same as an integral. So we could just create we could essentially draw functions to match these series if we wanted. But the sort of logic behind it holds in both cases. So we have essentially one series trapped inside another series, right? If we think of the series as area of a bunch of rectangles. All right, so let's do a couple examples. We're going to determine if a series converges or diverges. We'll go ahead and start off with the series, which is the sum from n equals 1 to infinity of 1 over the square root of 4n squared minus 1. And so note that the square root of 4n squared minus 1 should be less than or equal to the square root of 4n squared, which is just 2n, right, for n greater than or equal to 1. This means that 1 over the square root of 4n squared minus 1 must be greater than or equal to 1 over 2n. The inequality flips when we flip to the reciprocal, right? So essentially what we have is we can take our a sub n to be 1 over 2n, our b sub n to be 1 over square root 4n squared minus 1. We have 0 is less than or equal to a sub n is less than or equal to b sub n. And we know that the infinite sum from n equals 1 to infinity of a sub n, which is just 1/2 the sum from n equals 1 to infinity of 1 over n. We know this diverges. And so therefore, since this is our inside series, we also have that the sum from n equals 1 to infinity of b sub n, which is what we were given, the sum from n equals 1 to infinity of 1 over the square root 4n squared minus 1. This also diverges. So this is an example where we have divergence. Note, in order to prove divergence, we need the inside series to be the one that diverges. Okay. Now let's determine whether the series, which is the sum from n equals 1 to infinity of 1 over n squared plus n, converges or diverges. So again, note n squared plus n is greater than or equal to n squared for n greater than or equal to 1. This means that 1 over n squared plus n is going to be less than or equal to 1 over n squared. Again, flipping our inequality when we flip to the reciprocal. So if we set a sub n to be 1 over n squared plus n, and b sub n to be 1 over n squared, we again have 0 is less than a sub n as less than or equal to b sub n. And we know that the sum from n equals 1 to infinity of 1 over of b sub n, which is the sum from n equals 1 to infinity of 1 over n squared, converges. Right? This is a p series with p larger than 1. This means that we have the outside series convergence. And therefore, the inside series must converge. So we have that the sum from n equals 1 to infinity of a sub n, which was the sum from n equals 1 to infinity of 1 over n squared plus n, converges. Just a quick note. If 0 is less than a sub n is less than or equal to b sub n, if the sum from n equals 1 to infinity of a sub n converges, this tells us absolutely nothing about the series in B. So if the sum from n equals 1 to a sub n, or to infinity of a sub n converges, this tells us nothing about the sum from n equals 1 to infinity of b sub n. It could converge, it could diverge. Similarly, if the sum from n equals 1 to infinity of b sub n diverges, this tells us nothing about the sum from n equals 1 to infinity of b sub n. Sorry, about the sum from n equals 1 to infinity of a sub n. So sometimes you'll pick the wrong comparison, right? So if we had happened to compare this first series, if we'd happened to compare its terms to some series that had smaller terms, and that series happened to converge, that would be no help to us, right? Sorry, a series that had larger terms, and that series happened to diverge as well, that would give us nothing. So this one we did compare to one that had smaller terms which diverged, and so it was useful. But if we had gone in the opposite direction, also gotten something that diverged, it wouldn't help. So it's extremely important that you check whether we're working with the inside or outside series and which one that tells us. Right? We do have these two situations where we get nothing of any interest. So just make sure which statement we're working with, that your A's and B's match up. So just something to keep in mind as you go to use the direct comparison test. In the next video, we'll go ahead and look at the limit comparison test for convergence.